All right, so this problem looks more difficult than it really is. We have some given information about only one of the resistors, really. The other resistors, we know the resistance, but nothing else. So if I'm looking at this resistor, hopefully right away you notice you can apply Ohm's law and figure out the voltage or the potential difference across that resistor. So I'm just using Ohm's law, and the current is 4 amps, and the resistance is 1 ohm. Whoa, that's ugly. And we get 4 volts. Now it's important to always remember we don't know the voltage of this battery. That's what the question's asking. But if I follow any pathway, the voltage should drop all the way to 0. For example, if it's a 9-volt battery, you can imagine it starting at 9 volts, but after it's crossed all these resistors on this pathway, it should return to 0. Same thing on this pathway. After crossing how many resistors? Same thing, 3 resistors. I should drop from 9 to 0. Essentially what I'm saying is, whether I take the lower parallel or the upper parallel, either way, these voltage drops would have to be identical. That is, what if this voltage was 4 and this voltage was 2, the remaining 3-volt drop would have to come here, or if I took the other pathway, it would have to come here. So I, with 100% certainty, without doing any math, I know the voltage drops across those resistors in parallel must be equivalent. So this 4-volt drop is actually the same here. What does that allow me to do? It's just going to allow me to figure out the current going through this resistor now. What's that going to get me? This is a long roundabout way of figuring out the total voltage, but you'll see in a second. I already know the current going through here. What's the current going through that 2 ohm resistor in parallel? Well, I'm going to go ahead and use Ohm's law again, but again, now it's specific to this component. So current is equal to the voltage drop divided by the resistance. The voltage drop is the same in that parallel resistor because those are in parallel. So I get voltage divided by the resistance, and I get a current of 2 amps. Again, this might seem like irrelevant information, but I have just figured out that the total current in this circuit is 6. And that's going to be very important for figuring out the overall or total voltage, i.e. the voltage of the battery. So what do I know now? Now I know this is 2 amps on this lower part of the parallel, and this was given originally as 4 amps across this, or sorry, through this resistor. In total, you know that this circuit, for example, here, or let's say here, or passing through the battery, the total current, right? The total current would be the sum of all the branches or the junction rule, whatever you want to call it, or whatever you want to think of that as being. The total current is 6 amps. Now comes the final part. How can I figure out the total? I should have a little delta symbol there to be thorough. How can I figure out the total voltage across that battery, or the potential difference of the battery? Well, if I use Ohm's law yet a third time, I can solve pretty straightforward in a pretty straightforward manner using this. The only difference is I figured out the total current. I don't know the total resistance, but you hopefully know the rules for calculating total resistance. All right, so we now have the total current right here. So to find the total voltage, all I'm missing is my total resistance. Let's go ahead and find that. The total resistance in this case, well, you know the current has to pass through this resistor and this resistor. And those are in series. So hopefully you remember that resistors in series rule. I can just add those. That is no different than saying that, all the current is going through the zero point 0.5 resistor and the 2 resistor. So the resistors in series is going to account for a total of 2.5 ohms of resistance. If I look at the section here, sometimes it's called equivalent resistance. It's like saying, that kind of blocks out the writing there. It's kind of like saying, like, what is this section equivalent to in terms of resistance? All the current is going to pass through either the upper or lower part of this circuit. So it's almost like I'm going through 1, 2, and then 3. 1 and 3 are easy. How much resistance is this parallel chunk going to contribute? So resistors in parallel, remember, it's the inverse of the resistance in parallel if we use that equation. And again, that's a bit of a little derivation using actually the total current rule. It's actually a little derivation of this and Ohm's law. We don't need that. Let's just go ahead and use that formula. So the reciprocal of resistance, those resistors in parallel, 1 over the 1 ohm resistor plus 1 over the 2 ohm resistor. When you solve for resistance P or resistors in parallel, you do get 1 over, it ends up being 3 over 2, but you have to reciprocate. You have to flip that fraction. You end up with 2 over 3 ohms. Now remember, that's just this little, what I've got, a little cloud here. That section here is going to account for 2/3, or if we want to stay consistent and use decimal numbers, I'm going to call that 2/3. Oops, sorry, not amps, ohms. So I now know the total resistance is 3.17. 3.17 ohms. When you go ahead and punch that in, now I can use these values because this is the total current and the total resistance. When you multiply those values, you do get 6 times 3.17, and you get a lovely answer of 19 volts. Not an easy problem. A lot of the things you have to solve for seem like you're going off track. For example, finding the current through this resistor may have seemed irrelevant, but in reality, you can't figure out totals like this, like total voltage, until you know the other totals in itself. So that's a bit of a clue. If you need to find the total voltage, you probably need to know the other totals. This problem is pretty straightforward. It is basically just the junction rule. Um, if it's a 10-volt battery with a current of 15 amps, then you should be able to understand that these are all equivalent voltage drops as well across these 3 resistors because they are in parallel. So any one of these 3 pathways, 1, 2, 3, to get back to the battery, for example, any of those pathways are all going to have a voltage drop of 10 volts. That's important to understand. Now you should know current divides or splits when it branches, not always equally, but in this case it would split exactly equally. Why is that? The resistance is the same in all 3 pathways. So if each pathway has the same amount of resistance, you can imagine a perfectly equal split. If I have a total current of 15, right, the current here we're saying is 15 amps, you can expect 5, 5, and 5 going through those 3 pathways. So this problem, all in all, if you can just track the notation that they've given you the answers in, this one is not terrible. I1 is 15. I don't see that here. That's impossible. That's saying they're all equivalent to 5 when really I1 is 15. It's the total current. Remember, total current would be anywhere prior to branching. Or if there's a junction, it would be like after they rejoin. So really anywhere along my shaded blue line here and through the battery would have a current of 15 amps. However, as I discussed earlier, the branching, the split, this is 555. I2 should be equal to I3, which would be equal to I4, and those are all going to be equal to 5 amps. If I look here, I see a 2.5 amp, nothing should have 2.5 amp. The only possible answer here is C. This one is not a trick question, except it is weird because there are two batteries or two cells. I think this is pretty logical though, assuming that the current would flow towards the bottom of the page, right? Eventually the current has to, pass through that side of the battery, and the current, you could imagine it flowing, almost splitting here and going towards each, of these two pathways back in those loops. So obviously at this moment, the currents join like any junction. We've got 0.5 plus 1.5 for a total current of 2 amps, and down towards the bottom of the page. Down towards the bottom of the page. So 2 amps towards the bottom of the page. That looks like option D. Number 4. This one is not the most simple problem, but it's not terrible either. That equation for the resistivity of a material, resistance is directly proportional to the length of the material, L, and it is inversely proportional to the cross-sectional area, A. It doesn't have to be a cylinder, but generally with wires, it's easy to imagine a cylinder. So for example, you could have to find the area of a circle. How could they estimate the resistivity? So this is what I'm looking for. Okay, well, what could I graph? Well, right away, something that's screaming at me. If the good old y equals mx plus b, we want to know, if you pause and read this question, what are we looking for? We're trying to get resistivity from the slope of the graph. The way this question is phrased is really, we want to get the slope of the graph without having to do any other calculations. It says only the slope of the graph. So literally, I want slope to equal resistivity. Okay, so this is clearly what I need on my y-axis, and this would clearly be what I needed on my x-axis, because then I'm in the nice format of y and x, and there's my slope. So that's easy. So I just need a graph of resistance versus length over area. Easy. This problem's done. The small little trick here, Ohm's law. If you took any given voltage and current, and if you take that ratio, you will always get the resistance. So this is an indirect way of saying it's the potential difference over current. If you graph the potential, if instead of measuring resistance in your experiment, you took the voltage drop across, for example, across your chunk of wire, if you took the voltage or the potential difference across that chunk of wire and you divided it every time as you were varying the length and the area, for example, if every time you got these values, you just divided them or took this ratio, it would be the exact same thing as directly measuring the resistance. So just really, this isn't terribly difficult if you can recognize that, hey, hang on a second, I don't see R in this equation. Oh yeah, resistance is just voltage over current. Okay, how would different values of resistance affect the total current? Really, this question only has two plausible options, A and D, and even then quickly you can eliminate A. This would not be a measure of total current, nor would this. Okay, a good trick for total current is like there can't be branching, because we know that if this total current was 4, there or there, then these branches might be 1 and 3, or they could be 2 and 2, but the total current will never be on a single part of a parallel. That is important to remember. So this can be eliminated because this would not be the total current. So this would not be a great way to run this experiment. And same thing, not that would not be a measurement of total current. It would only be a subsection of the total current. This I could eliminate pretty quickly because it is in series. So how can I'm not investigating, obviously. Um, I'm not investigating circuits in parallel at all using option A. Option D, this location is in fact the total current, and I could, run my experiment by tweaking these two resistors, modifying the resistance in them. Number 6, the last one. This one is a little bit tricky, but I think if we break it down, it's not too bad. So this is a bit weird. You could sketch out a parallel circuit if you wanted, and you could imagine um, that sort of scheme. But really, if they're in parallel and it's a 3-volt battery, I guess let's just sketch it. Why not? If it's a 3-volt battery and the bulbs are in parallel, you'd get something like this, right? Oh, wait a minute, 3-volt battery, that means no matter which pathway I take, I should have a 3-volt drop across my resistor. So this is weird. I have a 3-volt battery or 3-volt cell, and each of these bulbs would also have a 3-volt potential difference across them. Why is that valuable? Well, let's just look at this. This is how I solved this. I'm sure there's more than one way to interpret this, but there are two lines, right? Let's pretend this is bulb 1 and bulb 2. The graph above shows current as a function of potential difference for two different filament lamps. This is almost like saying this is my lamp number 1 and this is my lamp number 2. Let's investigate that graph if I had, in fact, this 3-volt scenario. 3 volts right here. Okay, so when this bulb has a potential difference of 3 volts, the current passing through it is 0.6. Okay, so I have 0.6 amps passing through. What about this one? What about this bulb here? Well, that, again, when there's a potential difference of 3, the current passing through it, I've taken some data maybe, or I've recorded, the current passing through there is 1. So the current is 1 passing through bulb number 1 and 0.6 passing through bulb number 2. The total current would have to be the sum of those branches. So the total current in this scenario would be 1.6. How did I notice that the bulbs, again, how did I notice that the bulbs at 3 volts and look at this part of the graph? Knowing that them in parallel, they would have to both have a potential difference equal to the voltage of the battery.